Hello and welcome. Today we are entering into second lecture of alkali metal chemistry. Guys, are you able to hear me? Raise your hands. And is it being recorded? Do you see the record button on? Yes. Now, we had in the last class, we had discussed the general trends in physical and chemical properties of alkali metals. There are halides, there are oxides and hydroxides, and the anomalous property of lithium and all that. But today we shall be taking up individual chemistry of sodium potassium. Sodium is a very common element. So many minerals and ores are available, like chili saltpeter, salt cake, rock salt, borax, also called tinkle. It is the decahydrate of sodium tetraborate. Trona, it is a double compound of sodium carbonate and sodium bicarbonate dihydrate. So, and many others. And we already know these S-block elements and aluminum, they are extracted by electrolytic process, not by any chemical reduction process, because that is not economical. This is economical, because these are themselves very good reducing agents. And to use an elevated temperature condition to bypass the standard state and make the chemical reduction happen, you will have penny-wise, pound-foolish type of situation. So nobody does chemical reduction. Electrolytic method is the best choice. Now, sodium is extracted by Downs cell, electrochemical cell, where a mixture of sodium chloride solid and calcium chloride solid is melted, and the melting point is 600, less than the melting point of pure sodium chloride. Pure sodium chloride melts at 800 degrees Celsius, while this mixture melts at a 200 degrees Celsius less. And the question is, why calcium chloride is mixed? Obviously, to lower the temperature and reduce the cost. That is okay. That is a secondary reason, or maybe a tertiary reason. Of course, important reason, because finance, economics is the hallmark of our sustenance. But had we spent a lot of money for the electric bill, even then it would have been impossible. Why? Because at 800 degrees Celsius, sodium will vaporize. It is near to its boiling point. It will vaporize, and the vapors cannot escape out. It will condense inside the molten sodium chloride and form coarse sodium colloidal particles. Coarse colloidal particles, which will prevent the flow of ions. The electrical conductivity will be immediately stopped because of the colloidal particles of sodium. And moreover, it is very, very difficult to isolate the colloidal sodium from that particular mixture. That is why 600 degrees Celsius, economics wise good and otherwise also good, and it happens very smoothly at the proper discharge potential. You'll be knowing in your electrochemistry next year, I mean in class 12, at the proper discharge potential, the sodium is produced at the cathode. Sodium is produced at the cathode, and chlorine gas is obtained at the anode. And to prevent the mixing between sodium and chlorine, there is an iron, separator. Now, this is a cylindrical iron or steel cathode. This is the transverse section, and it is better seen here. The chlorine gas is allowed to escape in a different outlet. Sodium metal is siphoned from the cathode compartment to another chamber. So the cathode and anode, they are separated by the anode itself, which is made up of iron. This is the middle one, the carbon, the graphite anode, which will produce chlorine that will escape here, and sodium will come out. This is simply molten sodium chloride, and calcium chloride has been mixed only to lower the melting temperature, so that many things will happen. The disadvantages will be overcome. You might wonder why calcium will not be deposited, because the potential, the discharge potential that is selected for the electrolysis is only for sodium, not for calcium. They calculate what is the discharge potential for sodium. You will be doing that in your class 12. So calcium will not be deposited, rather sodium will be deposited. Now, this is the down cell, electrolytic cell. Now, coming to some of the properties of sodium, which we all know from these general trends, this is just a revision exercise. Sodium predominantly forms sodium peroxide, although the minor product is oxide, but the major product is peroxide. Of course, it displaces from cold water hydrogen. This is the new thing that I have not told. When sodium reacts with ozone in the liquid ammonia solvent, it produces sodium ozonide. That is the way to store ozone in the form of sodium ozonide. And at our need, we can just heat it and get back ozone. Sodium is such a strong reducing agent. It can displace many other metals and non-metals. It can displace silicon from silica, can displace carbon from carbon dioxide, and it will produce sodium carbonate. And look here, this is a redox reaction. You must, I told you, whenever you study inorganic, bring a pen in your hand and rough sheet to ensure whether it is redox or metathesis. If redox, then if some element has been reduced, some element has been oxidized, that you have to ensure. Maybe some multiple oxidations or multiple reduction, doesn't matter, but at least one of each type should be there. And then you attempt for balancing. I have already balanced for you, and here I tell you that sodium goes from 0 to +1 and carbon from +4 to 0. But here it remains also as +4 in carbonate, but it comes to 0. Then sodium combines with hydrogen to form hydride, chlorine to chloride, and any other element. So I have avoided superfluity, unnecessary things I have avoided. In this lecture or in subsequent lectures, I will not give you things which will intimidate you. I tell you that if you want to study inorganic from any textbook, I will recommend all books are good. They are flooding in the market, one competing over the other. So if you pick up GRB, it's a good book, but it is intimidating. Even a very, very bright students will see the chapter alkali metals, you will be simply intimidated. There is no necessity, because things are to be studied so many times in different chapters that there is no need to write everything of a particular element or metal. It's not necessary. So therefore, I recommend, while I say that the book is the best one, GRB, at the same time, I have recommended that you study the simplest book, that is NCERT, right? And the materials that I will provide in my lecture, or anyone, I don't say anyone who gives a concise note, not a very intimidating note, which you'll be scared to have such a extensive note. It's not necessary at all. Now, ammonia, we had already studied that. If you don't put any catalyst, you will form a blue solution. If I ask you what is that blue solution, you will say it contains ammoniated metal ion and ammoniated electron. But once you put a catalyst, then it will produce hydrogen and sodium amide. So also with dilute acids, it will produce hydrogen. And with nitric acid, it will produce one of the oxides. And I've taken dilute nitric acid, it will produce nitrous oxide. And I have done this balancing by ON method, say nitrogen from +5 to +1. The change is 4. It was previously 4. Sodium from 0 to +1, so nothing. Then after immediately, since it is N2O, I immediately made it 2HNO3. Immediately made 2HNO3. Only to look for N2O. Then I counted there will be extra 8 nitrate ion from the right side as spectators. So that has to be made up with this 8 plus 2, 10, and accordingly 5 water. So you must keep a habit of, balancing redox reactions by ON method or any other method which is best suitable to you. Now, this is another important reaction with carbon monoxide. Carbon monoxide, it doesn't reduce to carbon. It is further reduced to carbide, where carbon has a oxidation number of -1. This is acetylide. There is a triple bond here, C2, 2-, so carbon is -1. Acetylide. That kind of carbide. So it is not reduced like this. Here it is reduced to 0, but here it is reduced to -1. Sodium, as usual, 0 to +1. Carbon from +2 to -1 in sodium acetylide. So this is an important reaction you must remember and write down. Uses of sodium, this sodium lead alloy, this was being used to prepare the TEL, tetraethyl lead, by this equation. Nowadays, the use of TEL as an anti-knock additive in petrol has been banned. So no need to study. And as a reducing agent to, extract or to get several elements, including silicon, we have seen titanium, germanium, magnesium. So whichever they are less reactive than sodium, sodium can be used as a reducing agent to knock out them from their salts. And preparation of many compounds of sodium that we shall study. Now coming to the most important compounds of sodium hydroxide is NaOH, caustic soda, or also called lye. Not the opposite of truth. It is LYE, lye. Are you able to hear me? Please raise your hands to make sure. Hands down, please. Hands down, please. And is it being recorded? Can you see the button? Record button? Yes. Okay, hands down. Why I'm asking? Because that didn't shout. That is why I am asking you. Because if that is not done, then the entire exercise will be futile. Doesn't matter. Not futile, because I am there for you. But in one stroke, if you can kill 2 birds, don't kill birds, then it will be really, really rewarding for me. Now, sodium hydroxide was being manufactured by different techniques, different methods. The old methods have been totally redundant now. So we'll be taking the latest methods, how sodium hydroxide is manufactured by electrochemical method, by electrolysis method, that is called chlor-alkali process. There are three types of chlor-alkali process that are being used. The most widely used chlor-alkali process is the membrane cell method. In all these methods, brine is used as the electrolyte. Brine means in all these, brine is used as the electrolyte. Brine means sodium chloride solution, may it be seawater or whatever. And sodium chloride solution is taken as the electrolyte. And in this membrane cell method, I show you this diagram. I have borrowed from the that is a Google source, that there are two chambers. One is the brine chamber. The other one is the water alkali chamber, and they're separated by membrane, which will selectively allow the passage of some ions and prevent the passage of other ions. That is the ion selective membrane. This is made up of, thin plastic, of very, very sophisticated nature. They're being tailor-made to perform this task. Now, what happens here when you keep brine? This is the brine, a saturated solution or a concentrated solution of sodium chloride that will go here, and it will be coming out as a depleted brine. The percentage or the concentration will be less because some part of sodium chloride has been electrolyzed. Particularly, chloride ion has been oxidized to chlorine in anode. This is the anode, well, having the positive electrode. And the sodium ion thus left out will be heading towards the other chamber through this membrane, which will not allow the flow of OH minus ion from this chamber to this chamber. Rather, it will do the opposite. Sodium ion will go here and sodium hydroxide will be produced at this chamber. On the other hand, water will be continuously coming here, and water will be, of course, there will be initially some electrolyte, some sodium hydroxide must be used as a initial investment. Then after that, you fry your fish in the oil of the fish and eat fried fish. Now here water will come, and water will be, reduced at the cathode to produce hydrogen. Hydrogen will go away, and OH minus ion of water will be left out. This will be waiting for Na plus to arrive, and this compartment will become neutral sodium hydroxide that will be siphoned out in this particular outlet. So that is the best method, where you use a membrane and brine as the main source, which will provide the Na plus, equivalent amount of Na plus that will come here, and here it will produce hydrogen. But you see what happens here. In this, chlorine is formed at the anode in the brine chamber, and hydrogen is formed at the cathode in the water NaOH chamber. And Na plus selectively passes through the membrane from the brine chamber to the water NaOH chamber to mix with OH minus. And this is the overall cell reaction. The brine with water give you NaOH that ultimately is found in the cathode compartment. And chlorine in the anode, it goes out as a chlorine gas, and hydrogen goes out in the cathode compartment as a gas. But the disadvantage here, the NaOH still contains some, some chlorine also escapes and remains dissolved, of course, as sodium hypochlorite and sodium chloride. So that has to be removed. That is the disadvantage of this method, that some chlorine always remains with sodium hydroxide, because we are studying today sodium hydroxide chemistry. So that has to be removed. But the other method, though there is no impurity in sodium hydroxide, it's pure, but it will be a pollution risk method. So increasingly the governments are banning this mercury cell method. Kastner-Kellner cell or process is being increasingly, not encouraged, although it produces purer sodium hydroxide. Here you take mercury as the cathode. That is the interesting thing. Here you take mercury as the cathode. That remains floating in the bottom part of the electrolytic cell. The bottom part is a floating mercury, and that will be siphoned. Now what happens in mercury? In the presence of mercury, the reduction potential of sodium ion to produce sodium amalgam becomes more than hydrogen ion. It comes above hydrogen. Had there been no mercury, then Na plus has no role to play. It is water, the H plus ion from water, that undergoes reduction. But here, mercury is a player, and that makes the reduction potential even higher than 0. And that is why it produces sodium amalgam. And that amalgam now is siphoned, and it is allowed in a separate chamber with water. Fresh water reacts with the sodium amalgam to produce sodium hydroxide. That goes in another outlet. Mercury is set free to be siphoned back to the same electrolytic cell in a cyclic manner, and hydrogen escapes out here. And of course, the graphite and the anodes are not graphite, it's titanium or iron. But cathode is mercury. Cathode is mercury, which is sitting at the bottom of the electrolytic cell, and that is the cathode. And the anodes are the titanium rods. They are suspended inside the brine, right? So, but this handling of mercury, produces a lot of mercury vapors to the atmosphere. That is a serious threat to mercuric poisoning or mercury pollution. That is why it is being discouraged. Now the other method, little cheaper method, but a lot of impurities are there. It is very similar to the first method, membrane cell. Instead of a polymeric ion permeable membrane made up of polymers, very specialized polymers, the name I have given, Nafion, Plemion, Aciplex, they are very sophisticated and costly polymeric films. But this is a little cheaper, where instead of the polymeric membrane, you take a graphite, asbestos fiber. I'm sorry, asbestos, a separator, which is made up of asbestos fiber to separate between the two compartments, but the principle is same. That is called the diaphragm cell. That is called the diaphragm, not the membrane. It's a bit thicker, and it also does the same thing, but the efficiency is much better in membrane cell method. So these are the three latest methods. Now in the textbook, you'll find, not your NCERT, but in others, you'll find so many historical, methods which are of no significance now. Simply a student will be intimidated. I don't want that. You should be like that and study inorganic chemistry with much pleasure and enjoyment, picking up a pen and paper to make sure that what is happening, why it is happening, the logic. Now this is a very interesting reaction which will surprise you. Ordinarily, one cannot believe that a magnesium will be able to throw out sodium from a sodium compound, because magnesium lies below sodium, but it happens. It doesn't in the standard state. But when both are solid, sodium hydroxide solid, the pellets it is available in the form of pellets. I'll tell you the physical properties. Magnesium, make it a powder. Mix this magnesium powder with sodium hydroxide granules and grind them together very, very, then you heat it strongly in an iron retort. It's not that an easy job. You take a test tube and heat. Take an iron retort, even though it's made up of iron, and then heat it for a long time. You will find this reaction will happen at a other condition. So the the order that you have studied in your class 10 or class 9, that is only at the standard state. But later on you will study that even aluminium can displace magnesium at some other condition, other higher temperature condition, where the reaction becomes spontaneous. But you can appreciate that when delta G becomes negative, then things happen. If at standard temperature it doesn't, delta G is positive, then at some other temperature delta G might be negative. So this happens. So to recover sodium, immediately it is mixed with kerosene. So kerosene will make this soluble, but not this soluble. So, and hydrogen will go away, and it will make an explosion. As I'll show you an experiment. Thanks to the author of this experiment, I'll show you an experiment here. You have a glimpse of the experiment, what is happening. I'm just taking a bit of rest.
Okay, just preparing for making sodium. Just a try.
Are you able to hear?
There's a retort. There's a retort, and this is magnesium, and this is magnesium channels. You can see here. I'll open it. Channels. This one. Magnesium is NaOH, caustic soda, NaOH. These are the reactants. This is a lamp oil to capture the vapor, and this is a beaker.
This is the kerosene oil. This is the lamp oil.
Okay, these are the reactants. This is magnesium with NaOH, and then I'll mix it. Okay, so then I mix it.
It's not magnesium granules.
In tubes, the mixture now close it down, and close it, and fix it firmly. Firmly, okay. Now I'll put some lamp oil into the beaker. This is now on a brick, placed in the brick. This is the lamp oil, so put the lamp oil on. Now turn it on.
We'll see how hydrogen will explode. A large buildup of hydrogen concentration and a lot of flame is inside. So it will catch fire because it is combustible. And then, well done, that was an explosion of hydrogen gas. Sodium metal is, a lot of sodium metals are there. It is not soluble in kerosene, while magnesium oxide is soluble. Magnesium oxide has a large covalent character, Hajan's rule, soluble by sodium. Now we will show some sodium also inside he will show the presence of some sodium inside that iron retort. By putting some of the granules left out on the water, magnesium and sodium hydroxide will not produce any flame or any hydrogen. But now some of the remnants, residual things from the inside of the iron container is taking up and then putting in water and finding there is a glow. That means hydrogen is coming out and combusting. So that is the way. It's a very interesting way how you can get sodium. I am teaching you in the connection with the properties of sodium hydroxide. It can also be, it would have been discussed in the preparation of sodium, the laboratory method of preparation of sodium from sodium hydroxide using magnesium powder. It's not a powder, it's granules. Okay. Then going to the properties of sodium hydroxide. You know, sodium hydroxide is available in bottles, plastic bottles, with pellet-like appearance or granules, pellets, and they are highly deliquescent. If you open it, then it will absorb water and dissolve in it. The readily also it absorbs carbon dioxide from atmosphere. It is soapy to touch. The melting point is high. It is a strong base and corrosive, soluble in water, and it is exothermic dissolution. Also soluble in ethanol, methanol, but less soluble than KOH. KOH is more soluble in organic solvents. That is why it is chosen mostly in organic chemistry. NaOH is not chosen. KOH is chosen as it is more soluble in ethanol, methanol. And it produces yellow stain in cotton fabrics. And in, that cellulose gets degraded by sodium hydroxide. That is called the mercerization. We'll not talk about that, the mercerization of cotton or cellulose. Now, sodium hydroxide being basic will react with an acidic oxide, carbon dioxide, to form either sodium bicarbonate or sodium carbonate. If it is, you take a dilute sodium hydroxide and pass CO2. Supposing you are passing CO2, first you get sodium bicarbonate. Why fast? That's it. It won't produce sodium bicarbonate. But you are taking concentrated sodium hydroxide, the pH is larger than this. Then CO2 will first produce sodium carbonate. At a higher pH, first sodium carbonate is produced, and when you continue to pass more CO2 at a higher pH condition, so that the pH will be reduced because carbon dioxide is acidic in nature, and it will reduce the pH, and at a lower pH condition, bicarbonate will again form. So low concentrated or lower pH, also bicarbonate. High concentrated, high pH, you will get first carbonate, and then bubbling carbon dioxide in excess, that will give you a sparingly soluble sodium bicarbonate. This is sparingly soluble, less soluble. While carbonate is highly soluble, this is less soluble. So it will appear as a turbidity. Right? So must remember what is happening. And similarly, if you take, instead of carbon dioxide, if you take sulfur dioxide, you'll get bisulfite. If you take concentrated or excess, then you get sulfite. There are two steps. Let us go for the redox reactions of NaOH, which you shall also study in the chemistry of chlorine and phosphorus and other elements in other chapters. Everything will be taught in multiple times in different groups. So why to intimidate giving so much of information in one chapter? Let us break it in installments, right? Now, chlorine reacts with cold and dilute NaOH or KOH to give you chloride and hypochlorite. That you know, where the oxidation number changes from, it's a disproportionation reaction from 0 to -1 and 0, 2 plus 1. And you can balance it easily by just inspection. But here you have to go through either the ion electron method, taking the ionic equation and then balancing the molecular, or you can go for the EBD method, the electron balance diagram method. So you'll get 0 to minus 1, 0 to plus 5. So that it's 3, 6, 5, 1, 3. You have to balance of your own. When you copy from this file, you don't copy the coefficients. Don't copy, you just write the equation. Even you don't write the equation, just write the reactants and formulate or propose the products and see whether it is correct or not. Using your level of understanding, the logic of reaction, you write down the products. So this is hot and conc. With phosphorus, it will produce phosphine. Phosphine gas is produced when phosphorus reacts with concentrated NaOH. And this is the balanced equation. You have to take the help of water. Phosphorus goes from 0 to plus 1. This is hypophosphite. And this is the garlic smell phosphine gas. Now silicon forms silicate and hydrogen. With sulfur, deliberately I have not written S8, otherwise the coefficients would have been alarmingly huge, intimidatingly huge. So I'm using this intimidating several times because I looked through to the book, I found so there was no necessity of giving 20 pages for a particular block. No necessity. And sulfur gives also disproportionated to 0 to minus 2, 0 to plus. I mean, in fact, thiosulfate, the average oxidation number is, plus 2. But it is neither plus 2. It is actually an average of plus 4 and 0. That from the structure of thiosulfate, the peripheral sulfur is 0 and the internal, the central sulfur is plus 4. So the average is coming 0. In any case, you must write the average here. So sulfur from 0 to minus 2, 0 to plus 2. So that is thiosulfate. That. And sodium hydroxide with boron gives metaborate. Sodium metaborate. Zinc gives zincate. Because there are the 4 metals, zinc, tin, lead, and aluminium. The metals also show amphoteric behavior. They also react with bases, strong bases, to give you zincate, metaluminate, and so on. Zincate is Na2ZnO2, but this is a cheating formula. The actual formula is Na2ZnOH whole 4. So accordingly, you balance it. But for general purpose, you may write this, but for examination point of view, you must write the correct one. Sodium zincate. Now, similarly, you can take aluminium, you get sodium aluminate. Some people call it sodium aluminate, but I call it sodium metaluminate because some amount of sodium orthoaluminate is also formed. Very small quantity. I have not written in this. In the balanced equation, I am not showing, but it will be formed. So that is why it is metaluminate. In general, both are aluminates, but this is meta, AlO2 1 minus, or AlOH whole 4 1 minus. This is AlOL whole 6 3 minus. Right? AlOH whole 6 3 minus. So the actual correct formula is aluminate is AlOH whole 4 single minus. Similarly, tin will produce its plus 4 state from 0 to plus 4 because the plus 4 state of tin is more stable than the plus 2. But lead will have plus 2 state. I have not done it for lead. We'll be doing next time, next phase. So hydrogen goes from plus 1 to 0, while tin from 0 to plus 4. But the actual formula of the sodium stannate, ATE, is SNOH whole 6 2 minus. Now, these are the metathesis of non-redox reactions, where no change of oxidation number will happen. Now, I'm showing you how precipitation will form first, and then with excess NaOH, the precipitate will dissolve, forming a soluble salt. For example, you take a zinc salt, maybe zinc sulfate, zinc chloride, zinc nitrate, add sodium hydroxide slowly, dropwise. You'll first find a white precipitate of zinc hydroxide. Then if you add excess of sodium hydroxide, then that will show the amphoterism to form sodium zincate that is soluble. Same thing will happen if you take aluminum sulfate or aluminum chloride and add slowly sodium hydroxide. You will find first the gelatinous white precipitate, and then with excess, it will form sodium metaluminate. If you come little fast, you will not see the gelatinous white precipitate. In order to experience and enjoy the gelatinous white precipitate floating inside, you have to add dropwise. You must have done the experiment in your school. And tin similarly first produces stannous hydroxide. This is 2,2. And then it forms stannite. That is soluble. This is soluble. And all these are soluble. This is a white precipitate, stannous hydroxide, but with excess NaOH, it is soluble. So once you practice, understand the logic and practice at home, write in your copies, then slowly and steadily when you complete the families, S block and P block half will be done in this class 11 up to carbon family. So you get a lot of insight how to write equations and do the honors, right? Now coming to again some other non-redox reactions, this I have already shown here. This is a repetition. This is a repetition, no need. If it is stannic, then it will form stannate. This is again, metathesis, +4, +4. If it is chromium, it is chromite, not chromate. This is, it will show amphoterism. This is +3, this is +3, chromite. Like metaluminate, this is chromite. This is plumbite. This is +2, +2. But if you take plumbic oxide or lead-4 oxide, it will form plumbate. And of course, this is an odd man out. There is no metal here. Ammonium salt, ammonium chloride, or any ammonium salt with any alkali like sodium hydroxide on heating, mild warming, it will produce ammonia gas. It's not a big deal, but we had left one thing. The metal itself also will form hydrogen gas and sodium plumbite. That's not plumbate. This is plumbite. There is a mistake in the book I found. Lead cannot go from 0 to +4. +4 is unstable. So this is PbO2 is highly unstable. And by chance, if you are getting some lead 4 oxide from some source, which is unstable, it can form sodium plumbate. Still they are unstable. This and this both are unstable. So lead, we cannot go to +4. It will be +2, so plumbite plus hydrogen. You balance this equation at home, unbalanced. Okay, is it going all right? Raise your hands. Are you able to focus? You have to focus, otherwise inorganic will be too monotonous, but I will make it too attractive. Now, this is another reaction of sodium hydroxide. When you bubble, see, when you bubble carbon dioxide gas under high pressure or allow CO gas to react with NaOH under high pressure, 5 to 10 atm and a high temperature, then it will form an organic salt, sodium formate. This is an organic salt, salt of formic acid, sodium formate. You also write the names of these compounds. I have not written. The unusual ones, not sodium nitrite, sodium nitrate, you write no. These unusual ones like hypophosphite. like that. Now, NaOH will react with a mixed anhydride. NO2, which is a mixed anhydride, will produce two salts, nitrite salt and nitrate salt, because NO2 produces two acids, HNO2 and HNO3, hence two salts. Same will be the case if you go for ClO2, chlorine dioxide, which is also a mixed anhydride, and it is the anhydride of chlorus and chloric together. So you will form sodium chlorite and sodium chlorate. Same. So this is +4 to +3, +4 to +5. Same as sodium hydroxide reacting with NO2. And with phosphoric acid, acid-base reaction will happen. If you take 1 mole, you get NaH2PO4. 2 mole, 1 mole, then Na2HPO4. 3 mole, 1 mole, then the normal salt Na3PO4. I have written for the normal salt, the complete neutralization, but you can go for partial neutralization, 1:1 or 2:1, right? So I have left it for you. I mean, you need not also write, because these things are very, very trivial. Now, coming to another important, we had completed sodium hydroxide caustic soda. Same is the case with KOH. We won't study again KOH and write the same thing. The only thing, the KOH little more as basic. As you go down the group, the basicity will increase. As the ionic character will increase, the metallic character will increase, and then there will be more and more solubility, and hence the OH minus ion concentrations will be more, and hence the base strength will be more. But all of them are strong bases. Out of them, lithium hydroxide is least basic. Now, sodium carbonate is a crystalline solid. You can crystallize with 10 water molecules. Sodium carbonate decahydrate, that is famously called washing soda. Now, it can be prepared by Leblanc process, which was primitive one. Nowadays, Leblanc process is obsolete. But you must know why, because potassium carbonate is prepared by this method. Not sodium carbonate, but it was earlier, before the ammonia soda process by Solvay came into practice. This was going on. And first, sodium sulfate is prepared. When rock salt or sodium chloride is treated with Kong sulfuric acid, you have two steps. Ultimately, you get sodium sulfate. The sodium sulfate is mixed with limestone and coke. Powdered limestone and coke, and heated strongly to produce black ash, and carbon monoxide goes out. So black ash is a mixture of sodium carbonate and calcium sulfide. So you take black ash and dissolve and heat it with water. So sodium carbonate will be soluble in water, calcium sulfide will not. Then filter it out, take sodium carbonate solution, crystallize it again, and it will form beautiful crystal of decahydrate. But that this you have already done in your class 10 program, but you must know with all logic now that Solvay ammonia soda process is now the modern method of getting sodium carbonate. Now there are 3 steps. First, there is a large chamber. I will show you that. That's not required. I will not show. It's not required. Ammonia and carbon dioxide will be bubbled in one chamber while there is water, containing water under pressure. So these 3 will combine to form ammonium bicarbonate. This is the first step. The ammonium bicarbonate will be taken to another chamber. It will be allowed to mix with brine, sodium chloride solution, maybe seawater. And there will be a double displacement reaction. All these 3 steps are non-redox. That will produce sodium bicarbonate and ammonium chloride. And I have already told you sodium bicarbonate has a very low solubility. So it will be forming a precipitate. Then you filter it out and heat it strongly, you will find sodium carbonate. If you don't heat, then you are interested in sodium bicarbonate. That is the baking soda. If you heat it, you are interested in the washing soda, as the case may be. Now, the raw materials for this is limestone and brine. You have to continuously use limestone and brine. But you need not have to worry for ammonia. Why? Because you may start with some ammonia, but once the reaction starts, then there is no necessity of ammonia. Ammonia is generated in the setup itself. See, the ammonium chloride, which is formed in the second step as the product, is taken out to react with calcium oxide. Calcium oxide comes from the decomposition of limestone. So limestone kills two parts. It provides carbon dioxide to the first step, and also the quicklime, which will react with ammonium chloride formed in the second step to produce ammonia. This ammonia is recycled to the first step. That is why ammonia is not required, not a continuous requirement. The continuous requirement is limestone. Although in this step also you get, in this step, third step also you are getting CO2, and CO2 is again recycled to step 1. But in any case, we have to take a limestone, because we need carbon dioxide not for for step 1, but also we need the preparation of ammonia from the product ammonium chloride. So limestone has to be consumed and brine is to be consumed in a continuous basis, and the actual byproduct in the solvay process is not ammonium chloride, it is calcium chloride, because all ammonium chloride is broken down to ammonia. So sometimes you are asked a question in examination in the solvay process, which is the byproduct. Product is sodium carbonate. This dies sodium carbonate. This doesn't remain, this also dies, and finally that remains is calcium chloride. So calcium chloride is the byproduct. Now coming to the properties, very simple properties. Properties, it is white crystalline solid, and it undergoes efflorescence, means it loses the water of crystallization to the dry air. 9 water molecules are lost spontaneously when it is kept kept standing on a dry air, not highly humid air, but relatively dry air. It will produce monohydrate, and the monohydrate still on strong heating, not strong, about 200 degrees Celsius, it will produce the anhydrous. But anhydrous is stable to heat. It doesn't undergo further decomposition. It's called soda ash. Like potash and soda ash, they do not decompose on heating. And the solution is basic because of salt hydrolysis. The carbonate ion picks up a proton from water, becomes bicarbonate ion and produce OH minus. And of course, bicarbonate ion will also pick up H plus ion to produce carbonic acid and OH minus ion. But the case is greater than the second one. So the OH minus ion concentration is calculated from the first step. Second step, the case is much lesser. We'll be doing the intricate ionic equilibrium problems involving all this in our subsequent class. And these are the non-redox reaction. If you add HCl slowly, you will first get sodium bicarbonate. You don't find any carbon dioxide evolving. We shall be doing that in our ionic equilibrium program. If you add slowly, then this is the first stage where you get sodium bicarbonate, no carbon dioxide. But another same quantity of HCl, if you add to this, the sodium bicarbonate now will give you carbon dioxide. Usually what we do, we add up and cancel sodium bicarbonate, and we write sodium carbonate plus 2 HCl gives you 2 NaCl plus you. That ultimately happens. But if you add in a very systematic and slow manner, gradual manner, you won't find the evolution of CO2. We'll know the physical chemistry aspect behind that. And I have already told you, when sodium carbonate you have solution, you add bubble more carbon dioxide in water, it will produce a precipitate. Sodium bicarbonate is sparingly soluble, you get a precipitate. And this is a very typical reaction where if you bubble SO2 with sodium carbonate solution, the S will remain here, C will go out, it will produce CO2. The logic of this reaction is this: a stronger acid can displace a weaker acid. See, SO2, both are weaker, but carbonic acid is much weaker than sulfurous acid. So a stronger acid can displace a weaker acid. That is the logic. Now, in the same logic, you can find it will also displace silicon. If you treat it with silica, then sodium silicate and carbon dioxide, because silica also is a stronger acid than carbon dioxide, silicic acid. And these are the simply precipitation reactions. These are all precipitation reactions where carbonate is precipitated as calcium carbonate, barium carbonate, and with sodium carbonates, again calcium carbonate. So these are the precipitation reactions. Many carbonates are sparingly soluble, they appear as precipitates. Sodium carbonate can be used to soften water, for laundering, cleaning purpose, manufacture of several compounds like soap, borax, caustic soda, paints, paper, textile, and whatnot. And this mixture, sodium carbonate and its brother, potassium carbonate, this mixture is called fusion mixture. It is used in the dry test, in charcoal cavity test, in qualitative analysis that you will be doing in your salt analysis program. Then let's see how many slides are left. Only 3 to 4 slides we'll be doing. I will not intimidate you so that you feel you only write what I am giving you in the notes and you understand. Don't yes, I told you, if you have time, you can read them, NCERT and the materials I provide. That will be good enough for the Indian students. If by chance a non-Indian student is watching this video, then you go according to your syllabus. But so far as Indian courses are concerned, and all the examinations that the Indian students are to face, most of the questions are from NCERT. Most. All JEE questions, NEET questions are from NCERT. And yes, in case of advanced, JEE advanced, they are unlimited, you have to study. And your experience will make you feel confident more and more. Now coming to sodium bicarbonate, which is used in baking soda. It is not baking soda, it's used in baking soda because baking soda only contains 30% sodium bicarbonate. And other starch, calcium, hydrogen phosphate, sodium, aluminum sulfate, all these things are there. So preparation can be done by solvay process, the first 2 steps. Don't go to the 3rd step. And also from sodium carbonate, you can add a pass excess of carbon dioxide. So it will produce the precipitate. It has lower solubility, sparingly soluble. It is also basic because of some salt hydrolysis, but it is less basic than sodium carbonate. The pH value will be less, sodium carbonate will be more. We'll be doing the titration curves for these experiments. And it decomposes on heating to produce carbonate and carbon dioxide. On heating, it produces carbon dioxide, water, and carbonate. It is a mild antiseptic for skin infections, used in cakes and pastries, as a baking soda, and also used as a source of carbon dioxide in fire extinguishers. Now coming to sodium thiosulfate, which is a bit intimidating. I'm sorry. I'm sorry for you, but never mind. You will understand, I will make you understand, and you will get a feel-good factor to study the chemistry of sodium thiosulfate. It is available in the market as a pentahydrate called hypo. And when I was a child like you, now you might be wondering how we are not children, we are men and women. Well, yes, young women and young men. When I was a young man, of course, I'm still a younger man. But when I was a young man, I was, finding the extensive use of sodium thiosulfate in photographic dark rooms. At that time, there was not digital photography. Camera, you were taking expose the reel, the photographic reels, and then you are developing in a dark room. So while the first developing into a negative, what would they call negative, then positive, then they were washing the reel, the exposed reel, in hypo solution for a long time in a dark room. Then things were coming out. Some dissolution was occurring, and I'll tell you the reaction. Dissolution will be occurring, and those portions will be of course, when you look in front of you, we will be looking like ghosts. But once they will be developed into positive plates, then we come out, you will come out as handsome and beautiful faces. Right, that hypo is sodium thiosulfate, .5 water. How can you prepare it? Either you can add excess sulfur with sodium thiosulfate and heat, it will become sodium thiosulfate. Or this is another very interesting reaction where take iodine in presence of sodium sulfite and sulfide. So here, what you find, sulfur is from +4. It remains as +4 here, because this is a fictitious +2. It is actually +4 and 0. But here -2 comes to, let us write down +2, and 0 to -1. So that is the real change happening. Sulfide, it is going to 0. But it's +4 is remaining +4. Doesn't matter. Look to the average, -2 to +2. Average 0 to -1. So you get sodium thiosulfate by this reaction. Now, sodium thiosulfate on strong heating, it will give you a very exotic compound, sodium pentasulfite, where sulfur is in the polysulfide state and sulfur is -2/5. Pentasulfite. It is a polysulfide type. Sodium sulfate, where sulfur from say average +2 to +6 and +2 to -2/5. And any dilute mineral acid like sulfuric acid and hydrochloric acid will produce SO2 similar to sulfite. Additionally, yellow sulfur precipitate. And this is a very, very important reaction. Remember this, that when thiosulfate reacts with iodine, it produces, iodine, the color of iodine is discharged. The violet color of iodine is discharged, and reddish brown color, I'm sorry. Because iodine aqueous solution is reddish brown, that is discharged. Of course, we finally add towards the last part, we add a bit of starch indicator, and that makes the solution blue. Starch and iodine forms a blue complex, and that blue solution vanishes. That is the end point. Now, sodium thiosulfate becomes sodium tetrathionate. Iodine becomes 0 to -1, and this is +2 average to +2.5 average. So this is a famous reaction which you have done much before during this is the iodimetry, where iodine is consumed in titration, taking thiosulfate as the titrant, as the titrant, and iodine solution as the analyte. Now, this is sodium thiosulfate reacting with silver nitrate. First, a double displacement reaction, giving you silver thiosulfate and sodium nitrate. And then after a bit, immediately you will find the white precipitate will turn black because water will hydrolyze it to produce sulfide and sulfuric acid. This will be a spontaneous reaction where there is a redox process. From the average +2, it will go to, from average +2, it will go to -2, and sulfur again +2 to +6. So this redox will be taking place spontaneously. After some time, the white precipitate will turn black. Now this reaction was happening when I was looking, my elder bro was a photographer. His hobby was photography. So he was much elder to me, and he was doing college, and I was doing middle school. The time I used to visit his dark room where he was developing the negative reels. So it's a typical smell, sodium thiosulfate, sulfur smell. And this, this is the silver bromide plate. And when this is exposed, then light reaction, it is forming some silver bromide will be there. And then you are washing it. So this will be washed out, forming complex. It is a monosulfato complex, dithiosul. This is thiosulfato complex. Sodium, you will be knowing how to name it. Sodium thiosulfato argentate 1. This is sodium dithiosulfato argentate 1. So if you take excess, then this complex. If you take less, then this complex. So silver chloride will be coming out of the photographic plate, and that portion will be only those which are exposed portion. They will be little delicate, and they will be undergoing this reaction. The other will not. So development of ghosts will be there in the photographic plate. So I'm not very, proficient about those things really taking place. But this is the reaction, chemical reaction. Similarly, chlorine water, that will go for a redox reaction where sulfur from +2 to +6, +2 to 0. This is the chlorine water will oxidize thiosulfate to sulfate in itself, and itself reduce from 0 to -1. So sulfur has undergone oxidation as well as reduction, but chlorine has undergone only reduction. There can be multiple oxidations, multiple reduction, as you know, but at least one from each category must be there. So this is an intimidating reaction where copper sulfate reacts with thiosulfate to first give you cupric thiosulfate metathesis. But here you have a redox reaction where copper from +2 to +1 happens, and sulfur from +2 to +2.5, just like in case of iodine reacting with sodium thiosulfate. So cupric becomes cuprous thiosulfate, and then cuprous thiosulfate with excess of sodium thiosulfate gives you a very big complex. A very, very big complex. This is sodium pentathiosulfato hexacuprate. Forget about it. And the uses of hypo is an anti-chlor. It removes chlorine by this reaction. Anti-chlor, it removes chlorine by this reaction. And it is used for the extraction of silver and gold by doing this complex. By doing this thiosulfato complex, fixing, that is what I was observing in the dark room. Fixing agent in photography and qualitative analysis, iodinometry, to estimate the amount of iodine produced in some iodometric reaction. Now, I fail to understand why I have not given this a interesting color, because I am a color master. Yes. This is a Glauber salt. This is available in nature as Glauber salt, but we can prepare sodium sulfate by any chemical method and then crystallize to form decahydrate. We can prepare sodium chloride with Kong sulfuric acid, and we can prepare sodium sulfate in 2 phases, sodium bisulfate and then sodium sulfate, and then crystallize. And interestingly, You remember this, sodium sulfate is soluble below 32.384. Below that, it will be more and more soluble. Lower the temperature, greater is the solubility. I mean, solubility will be maximum here, but then, I'm so sorry, solubility will increase at low temperature, become maximum at 32.384, and further heating, increasing in temperature, will bring about lowering of solubility. Its solubility decreases with further increase in temperature. This is a very important information about Glauber salt. The anhydrous salt is a drying agent and used in the preparation of glass and paper. This is sodium cyanide, the brother of potassium cyanide, the deadly poison. Sodium cyanide is equally poisonous, that can be prepared by, heating sodamide, sodium amide with coke. So here you find that the oxidation number changes from -3 to -2, and carbon from 0 to +2, and also hydrogen from +1 to 0. So there have been how many reduction? Nitrogen, nitrogen has undergone, and sorry, I'm so sorry. Nitrogen is -3. I'm so sorry. Nitrogen has not done any change. So let me rub it off. So hydrogen from +1 to 0, carbon from 0 to +2 here in cyanide. Now, even calcium cyanamide, cyanamide? This is cyanamide. It's a linear species. Carbon is sp, and that reacts with coke along with sodium carbonate. Heat, it will produce sodium cyanide and calcium carbonate. Properties, the cyanide ion is a fantastic complexing agent. It forms complexes, cyanido complex. For example, gold dissolves in sodium cyanide with bubbling air, oxygen, to oxidize gold from 0 to +1, and this is oxygen from 0 to -2. So it becomes sodium dicyanido orate 1. I can call it sodium orocyanide. Right, silver gives this similar type of reaction. It undergoes dissolves, forming cyanide complex. Copper sulfate with excess NaCl will also produce this one. We'll be studying the details in the copper chemistry in class 12. It first produces cupric cyanide, just the way you found in thiosulfate complex. It first cupric, then cupric becomes cuprous, and with excess cation it forms, or NaCN, it forms this +1 complex. Cadmium sulfate gives +2 complex, doesn't have variable valency. This is the cadmium complex. Sodium cyanide or potassium cyanide used in extraction of silver and gold, electroplating of gold and silver. Now, potassium, we are left with this, that is all. Now, potassium is similar to sodium in its all behavior. The ores are different. Carnallite, Indian saltpeter are called niter. Sylvite, KCl. So same electrolysis of fused calcium instead of sodium chloride here, potassium chloride, but the other impurity, calcium chloride, is the same, similar to sodium. Similar to sodium, except potassium with air or oxygen produces superoxide, like rubidium and cesium, not peroxide. KOH is more soluble in inorganic solvents, in inorganic solvents like ethanol and methanol. And potassium carbonate, it is called potass or perlas. This is prepared by Le Blanc process. You might ask me why the Solvay ammonia soda process is not applicable. So instead of NaCl, brine, we will take KCl. Same thing will happen. No, because potassium carbonate, bicarbonate produced in the second step is not sparingly soluble. It will not precipitate out, it will flow out. So you can't isolate potassium bicarbonate. It is highly soluble in water, unlike its brother sodium bicarbonate. So Solvay process is not applied. Rather, the same Le Blanc process is used, same steps, First, potassium sulfate is produced, heated with limestone and coke to produce black ash. This time it is potassium carbonate, and then extracted with water. This will be dissolved, this won't, and then you crystallize. It is a deliquescent. It will absorb potassium, absorb water and dissolve in it, and highly soluble. Other compounds of sodium and potassium, sodium chloride, potassium chloride, Ki, NaNO3, KNO3, KO2, these things you study yourselves at home, but not necessarily now, because they will be coming multiple times. The reaction of Ki, I minus is a very, very excellent reducing agent. With every oxidant, I minus becomes IO2. So why? Now to study much. Whatever I said, that will be good enough for our program. So I think it has already been 1.5 hours program, maybe very close to 1.5 hours. So we finish the alkali metal family, and in the next program, we'll be doing alkaline earth metals family. And you guys who are watching, following this program, we must not hesitate to put a thumbs up. And also, as I used to say, that you must not also hesitate to subscribe to the channel. Bye. Take care. Next time.